If you were here for Global Math Week last week, you know that we went through with MoMath, the Museum of Mathematics in New York, we went through all the lessons every day, twice a day, lots of times. Some of you were there for that, so hopefully this is excuse me, if this is a repeat lesson for you, it's exciting and fun. It's good to see things twice. But it is a standard lesson, and we believe exploding dots is for all year long. So we're going to keep offering these lessons over and over and over again. So if you have a class of students like we have in Mumbai right now to want to join, we are happy to give these lessons for you, fabulous, fabulous students. So let's see, it seems to be past the hour right now. It does. Are we ready to begin? And the answer has to be yes. So just someone nod and I will believe you. Did I see a nod? I saw nods. It's time to begin, which means I do my usual fumble with trying to make sense of Zoom as I try to share my screen. Morning. All right, here goes. Share the screen to get ready for lesson number 5 of Exploding Dots, which is going to be about division. Here it is. Hopefully you're seeing my screen, no worries at this point. And here's a whole collage of different photographs and activities from around the world all last week as people doing exploding dots. But here goes. To see the full experience, just go to globalmathproject.org. But here comes division. Here comes division today. All right, so a lot of people know a rule for divisibility by 9. For example, people know that a number is divisible by 9 only if the sum of its digits is also divisible by 9. For example, how does that work? So if I take a number like 387261, the rule says, I wonder if that's divisible by 9. The answer is, look at the sum of its digits, 3 plus 8 plus 7 plus 2 plus 6 plus 1. And arithmetic's not my forte. There's 10. There's 10. That gives me a 20. This adds up to 27. Oh, 27 is a multiple of 9, which according to the rule says that must be a multiple of 9 as well. And I'm actually going to check that with my calculator. 387261. Are you truly divisible by 9? If I divide by 9, do I get a whole number? Yes, I do. Yes, I do. In fact, you can see it for smaller numbers like 83. I know, oh no, that's not divisible. Now what I'm saying, 81 is divisible by 9, and the sum of its digits plus 1 is also divisible by 9. You see this all over the place. But actually, there's a much better and stronger rule than this one, which not as many people seem to know. It says this. A number leaves the same remainder upon division by 9 as does its sum of digits. Now, that one's a little bit hard to understand. Let me show what I mean. Actually, let's take 83, which I mistakenly wrote before. That is definitely 2 more than a remainder of multiple of 9. It's 2 more than 81, so leave a remainder of 2. And look at the sum of its digits. Sum of its digits is 11, which is also 2 more than a multiple of 9. It would leave a remainder of 2 if you divide by 9. 77 is 5 more than a multiple of 9, remainder of 5. And the sum of its digits is 14, also a remainder of 5. It's 5 more than a multiple of 9. Now let's do a crazy one. 40061. I don't know if that's a multiple of 9, but according to the rule, if I add up the digits, 4 plus 0 plus 0 plus 6 plus 1, that is up to 11. That has a remainder of 2 upon dividing by 9. So apparently that also has a remainder of 2. Okay, is that true? Let's get my calculator out again. Okay, 40061. 40061. If I divide by 9, I should get something that's not a whole number. In fact, it should be a whole number plus 2/9. 0.22222 forever is 2/9 indeed. It does leave a remainder of 2. In fact, we'll talk about decimals next week. But for now, I can see it does have a remainder of 2. Wow. And in fact, this is actually a stronger rule than we had before. We were talking about remainders of 0 before. A number leaves the remainder of 0 upon division by 9, that's the multiple of 9, only if the sum of the digits also leaves the same remainder of 0. So actually, if I just focus on the remainders of 0, this is the previous rule. This just focuses on remainders of zeros, but actually the rule is true for any remainder. The sum of the digits and the whole number itself leave the same remainder upon division by 9, even if that remainder is not 0. So here's the big question for today. Why does this work? So I can do it. Well, question mark. Oh, why does that work? Big, messy why. So that means we need to understand division. And that's today's focus, to understand division. And to get to division, I'm actually going to go with multiplications, what we did last time. So I'm going to pick up from last lesson about multiplication. For those that weren't here, don't worry about it. I will try to make this self-contained. So I take a number like 1302. All right, that's fine. It will look like this. If I imagine like a 10-1 machine is what I call it, exploding dots. A lot of people talk about place value charts or maybe do manipulators like 10 blocks and so forth. I've got ones, tens, hundreds, and thousands. I'm saying like 1,000, literally 1,000, 300, literally 300s. There they are. No tens, and 2. So there's the number 1,302 as a picture. Great. And suppose I said, please triple it. Please multiply by 3. Let's make everything 3 times as big. And what would I physically do in my picture? Well, 1,000 should become 3,000, which means I take this dot and triple it, make it 3 dots. This dot would also get tripled. If I'm tripling everything, this dot gets tripled. I triple everything, and if I triple everything, this dot also gets tripled. Also, this dot gets tripled, and this dot gets tripled. I was asked to triple everything, so I did. I tripled everything I saw. And now I see the answer 3,900s, still no tens, and 6 appear. So there's multiplication, literally triple everything, and I get the answer 3,906. But here's the interesting thing. Division would be doing this backwards. Suppose we didn't see that. Suppose I didn't do that. All I did was give you the answer 3,906, which looks like that. Suppose we start with the answer and say, hang on, James, can you figure out from your picture what 3,906 divided by 3 is? What got multiplied to give me the answer 3,906? If I think my way through that, well, I can actually see it from my picture. I see from my picture that, oh, something got multiplied by 3 to give 3,906. Well, there's a dot, there's a group of 3. That group of 3 must have come from one dot that got multiplied. So one dot got tripled. Right there, I can see it. Here's a group of 3. That must be from one dot that got tripled. There's another group of 3. There must be one dot that got tripled. There's another group of 3. There's one dot that got tripled. So there's 3 dots there that got tripled. No dots there that got tripled, but there's a dot that got tripled right there, and another one right there. So actually, I can see 1 dot in the thousands place got tripled, 3 dots in the hundreds place got tripled, and 2 dots in the ones place got tripled. Oh, this must be 1302 that got tripled. So actually, that means I've just done division. I've just done division. I looked for groups of 3, literally, where all the things got tripled, and I could see what it was that got tripled, 1302. All right, your turn. Just to practice this idea, I'll do an easy one, but draw me a picture of 426 divided by 2, and show me that really was 213 that got doubled. Can you really show me in a picture that 426 divided by 2 really was 213 that got doubled? Can you see that for yourselves? And let me just clean the page 2 so we can get a fresh page. It was 426 divided by 2. And yeah, I bet you've done it. 426. Was that something that got doubled? Yes. Here's a group of 2. 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 Yes, it really was 2 dots, 1 dot, and 3 dots that got doubled. By looking for groups of 2, I can see it really was 213 got doubled. Beautiful, beautiful. There is a possible hiccup though. Try this one. What would you have to do for this one, 102 divided by 2? I know the answer is 51, but what's the issue in drawing a picture of that one? And actually, since we're a small group today, feel free to unmute yourselves and just say out loud any thoughts you have about what we could do to possibly handle this beastly one. $100, no tens, and 2. And I'm looking for groups of 2. Oh no, what got doubled? There's a group of 2. One dot got doubled over there, but that's about all I can see. What could I possibly do? Oh, someone in chat said Jed. Jed said unexplode. Yes, yes, because this is really 10 dots from over here. 10 tens make 100. So 100 is the equivalent of sucking sound for unexplode, 10 tens, which is great because that now gives me lots of doubles to look at. Beautiful. A double dot, a double dot, a dot that got doubled, another dot that got doubled, and another dot that got doubled. Yes, 5 dots and 1 dot got doubled. The answer must be 51. In fact, there are 5 groups of 2 at the tens level, 1 group at the ones level. It really is 51. There's 51 groups of 2 in a picture of 102. Beautiful, beautiful, beautiful. Great. Well, then I believe that we are ready for more complicated division. 276 divided by 12. Let's do multi-digit division. We're ready for it. Okay. So let me draw a picture. Here's 276. I'll make it big and clear this time. 2 hundreds, 7 tens, and 6. All right, and we're looking for 12, and this is what 12 looks like here, but there's going to be a problem. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Because 12 dots in a box are not stable. Because society says you can't have 12 digits in a box. We need to actually do some explosions. And what happens here is that 10 ones or 10 whatevers, 10 of these, kaboom, we have to explode away, make 1 dot one place to the left and leave 2 behind. So 12 dots is really actually 12 dots right there, but kaboom, the spillage, 1 dot spills over. So the 12 dots are really in the rightmost box. Trouble is we write 1 dot next to 2 dots for those 12 dots. That is annoying. That is annoying. But here's the thing. In this picture of 276, we're looking for 12s. What dots got multiplied by 12? 12 looks like 1 dot next to 2 dots. Do you see 1 dot next to 2 dots anywhere in that picture? And you look at it for a while and you realize, yeah, there's 1 dot next to 2 dots right there. And you have to be careful, say, oh, goodness, where are the 12 dots actually? Well, the 12 dots actually must have all been right there, and kaboom, 1 must have spilled over. So there's the group of 12 dots right there. So that was really 1 dot became a group of 12, and then kaboom, spilled over. Whoa, so there's 1 group of 12 at this tens level. Any other 1 dot next to 2 dots in this picture? And you look at it, 1 dot next to 2 dots, right there. So there must be 12 dots right there that went kaboom, spilled over. So there's 12 dots right at that level that spilled over. Kaboom, 1 dot became 12 and spilled. Okay, any other 1 dot next to 2 dots? Anyone see any more?
How about 1 in the tens and then 2 in the ones?
Yeah, we can go over now. 1 dot next to 2 dots. Fabulous. Yes, I see it there too. All 12 dots must have been there and spilled over. Kaboom. So all 12 dots are literally there. Just that spillage is annoying. All right. And you know what? I bet we can see it again. Another 1 dot next to 2 dots. Fabulous. Right there. 12 dots. Kaboom. And oh, it's another one. My loop's getting really weird, but maybe that's okay. Really weird loop. 1 dot next to 2 dots. 1 dot next to 2 dots. Kaboom. They spilled over. So actually there's 3 at the ones level, 2 at the tens level. The answer must be 2 at the tens level, 3 at the ones level. That's what got multiplied by 12 to give me 276. And just to double check, 276 divided by 12, please be 23. Yep, it's 23. Wow, I love that. Okay, your turn. On your ownsies, but I'll leave it on the board first. I would love to know what 2783 is divided by 23. Can you draw me a beautiful dots and boxes picture of that one? 2783 divided by 23. I'll give us a moment and then I'll try it myself. Actually kind of cool. It's actually really good to do this on a whiteboard rather than paper and markers. Paper's so unforgiving. I think we're okay. Maybe we're okay with this. All right. 2783. That's what 27383 looks like. 2000s, 700s, 810s, and 3. 23 would be 2 and 3. So we're looking for 2 dots next to 3 dots. We have to remember all 23 dots are technically right there in the right part of the loop, but the rest we're going kaboom, kapow, 2 explosions to spill over. So we've got spillage again. Do you see 2 dots next to 3 dots anywhere in this picture? It's good to make weird sounds. There's a really weird loop. 23 dots right there. Kaboom, kapow, must have spilled over. All right. Any other 2 dots next to 3 dots? In fact, type into the chat if you think you know what the final answer is. I'm curious what people are getting. What final answer you get? I bet it begins with a 1. What sort of answers are people getting? Okay, one person said 121. 121. Maybe we're getting 121. Cool. If a third person agrees that, oh, 3 people agree, it must be true. All right, I'll do it too then. 2 dots next to 3 dots. Whoa, right there. 2 dots next to 3 dots. 1, 2, 3, like that. Oh, my loops are so strange. Yes, 23 there, kaboom, kapow. 23 there, kaboom, kapow. And then, oh, I was nice. I was nice. 1 there. Yes, this must be 1, 2, 1. They got multiplied by 23 to give the answer 2,783. We're doing division. This is awesome. Oh, I have a question. What have I asked for 2784 divided by 23? How would that change? What would change in the problem?
You would have a remainder 1.
Yeah, because here's 2783, but I want 2784 means I've got an extra dot. So what we'd see is this extra dot just sitting there thinking, oh, what are we going to do with that extra dot? And you would say, I guess the answer is still 121 with a remainder of 1. I believe in America, people write small r for remainder. In Australia, we had to write big R for remainder. I'm curious, in India, what do people write for, what's the notation for remainder in India? What do people do there?
We use R.
A big one or small
Capital
one?
R.
Capital R, capital R.
The uppercase. Yeah.
Uppercase, yeah. I think in Korea, I was told they use ... 1. I think some countries do ... The actual, by the way, the actual correct answer, the mathematical answer is 121 plus 1 more dot still waiting to be divided by 23. So that's the actual maths answer. It's 121 and 1/23. 1 dot still waiting to divide by 23. Either way, whatever style you like, there's definitely a remainder of 1. And if there are remainders in division, you will see them by this method. I love it. Okay, you guys are so brilliant. I'm going to give you a really tough one. Here is a challenge problem. 3182 or 4 divided by 102. Watch out for the number 102. It's tricky. Can you do this one? Okay, so people are getting answers. Okay. So we're a small group today, so feel free to just tell me stuff. It makes it easier for me. It's hard for me to read the chat and do all this. 312, people getting 312? Okay. 102 is annoying. 102 is annoying. It really should be 102 dots in there, but it's going to be so many explosions. Kaboom, kapow, kabing, blah, blah, blah. So many explosions that actually get 1 dot way over here, blank, 2 dots. So there's 102. So all 102 dots really are in the rightmost box, but there's a lot of spillage going on this time. All right, but in any case, we're looking for 1 blank 2. Apparently the answer is 312. I don't see it yet, but I will do it myself now to check. 1 blank 2 dots, 1 dot, no dots, 2 dots. I can do that. 1 dot, no dots, 2 dots, right there. All 102 dots must have been there and a lot of explosions spilling over. So all 102 dots really were there. Another 1 blank 2. I can see it. 1, I'm getting nervous. Can I just do this? 1 blank 2. Can I make my loops a little bit neater? Hopefully that's okay. 102 dots there. 1 blank 2. There again, it's another 102 dots. How am I doing so far? I think I'm doing okay. 1 dot, no dots, 2 dots. 1 right there. Can I keep going? Yes, I can. 1 dot, no dots, 2 dots. Another one there. 1 dot, no dots, 2 dots. Another one there. Yes, yes. This must be 3 dots, 1 dot, 2 dots that became 102s. That is, this is 312. 312 times 102 must be 31,824. Beautiful. Okay, okay. Then I'm going to give you the really tough one. Here's a really tough one. Try this one, and then I'll move on and talk about more stuff. But try this practice one. I have a feeling this is going to have a very big remainder. Try this one with a big remainder. Can you see what the remainder is in this one? Whoa, I'll make my dots bigger. So what sort of answers are we getting? Is someone there yet, or is this one just too tricky? $312 again. It seems like the number 312 today, with a remainder of 21. Yeah, I think that's what I did. Yeah, so 1 dot, no dots, 1 dot. 1 blank 1, there's 101. 1 blank 1, there's 101. 1 blank 1, there's 101. Uh-oh, keep going, keep going. 1 blank 1, there's 101. 1 blank 1, 1 blank 1, 101, 101. You're right, it is 312 with a remainder of 2 dots here and 1 dot there. So that's a remainder of 21, remainder of 21. Beautiful. So it's actually 312 and 21 101s. Beautiful, beautiful, beautiful. Okay, okay. I love this method of division. Now, people say to me, James, surely you don't expect me to draw dots and boxes every time I do a division problem. No, of course not. This is very long and tedious. It's fun. I love it. But here's what I have. I have in my mind every single time this picture. This picture is always in my head when I do long division. What I want to do now is talk about how I was taught to do long division as a kid back in Australia about 40 years ago. I'm an old man. About 40 years ago, let me do 276 divided by 12 again. Here's how I was taught to do division back in Australia. And it made no sense to me whatsoever back then as a 10-year-old, 12-year-old, however old I was. So let's see, 276, we had to write a very funny symbol like that. Very strange. We had to put the big number inside the symbol and the small number to the side of the symbol. Okay, this is weird. Now, I don't know if you remember, but in the previous lessons, I was talking about how everything in math class seems to be right to left. You always do things right to left. And I always say, no, just do things left to right and do explosions. I like left to right. Well, suddenly in year 5 for me, people said, no, you don't do right to left. You do this one left to right. So they switched directions on me suddenly in grade 5. After training me for 4 or 5 years to always go right to left in maths, teacher suddenly said, no, you go left to right, as though it was normal. I thought that was strangest number 1. Anyhow, we then had to look at the number and say, okay, we'll go left to right. Look at the number 2. Well, there's no 12s in 2. Don't be silly. Then look at the number 27. And then here's that strangest number 2 for me, because I said, hang on. the number's 276. You can't just say 27. You can't pull out bits of the number and call it 27. I thought that was weird. Nonetheless, I was a good student. I obeyed. I said, okay, we're going to look at 27. You say, how many times does 12 go into 27? And you think, okay, 2 times 12 is close, it's 24, but we had to actually write down 24. And then we had to actually write that 2 at the top. 2 times 12 is 24. Okay, fine. And then suddenly, out of the blue, in the middle of a division problem, we were told, just do subtraction. Do a quick subtraction problem. 27 take 24 is 3. That's bizarreness number 3 as a kid. I thought that was weird. So that's 3 bizarrenesses so far. But here comes bizarreness number 4, the thing that confused me big time. In Australia, we had to draw little arrows, bring the 6 down, and this 3 that I got suddenly becomes 36. It just changes. Just suddenly changes to 36. That is really bizarre. I had no understanding as a kid why we're doing that and why this worked, but I obeyed. Then you ask, how many times does 12 go into 36? Goes in 3 times, okay. Then we had to actually write 12 times 3 is 36. Then we had to do another subtraction problem, why not? And then we got 0, and apparently that was good. That's what I was taught as a kid. Whoa, and I did not understand it. Now, I got all my gold stars on my worksheets. I was a very good student. I did it, I obeyed, but I was very aware I didn't understand what I was doing. But today, I think I have the chance to understand. Because here's what we did. This is why I love having this picture in my brain. 276. There it is. And we're looking for 12. 12 was, remember, 1 dot next to 2 dots. All right, so what did the algorithm say? It said, okay, first look at the number 2, and you say, don't be silly. Well, that's what I did here. I looked at number 2, there's no 12s in there. And then they say, well, look at 2, 7. Oh, look at 2, 7. Look at this part of the picture. I will object to calling it 27. I don't think we're allowed to call that 27. It's just 2, 7. But what we really asked to do is look at 2 dots and 7 dots. And then we asked, how many groups of 12 do we find? In fact, we did it. We found 1 group of 12 there, 1 group of 12 there, and we wrote 2 at the top. And look, we wrote 2 at the top as well. We did the same thing. We did exactly that as well. Then this subtraction thing, what's it saying? Well, we looked at 2 dots and 7 dots. We used up 2 and 4 dots, which means we have 3 dots left over to play with. We have 3 dots left over to play with. That makes sense. We still have 3 dots to consider. Now, this weird thing about the 6 coming down and suddenly making 36, that is bizarre. All we're doing is say, now you've got 3 more dots to play with. Why not just reveal those 6 dots as well? Let's look at 3 dots and 6 dots. That's all it's saying. Look at 3 dots and 6 dots. And look, we'd earlier on found another group there, another group there, another group there. Woo! We wrote 3, and look, there were no dots left over. We have no remainder. So actually, this very bizarre algorithm I was taught back in Australia is actually just the dots and the boxes picture, and no one showed me a dots and boxes picture. I wish they did, because having this in my mind now makes perfect sense to that. So I'm curious, who in this room right now learned division this way? Yeah, I can't see everyone's hands. So lots of people, it looks like. Just type yes into the chat or no. I'm just curious. Yes, I learned it this way, or no, I didn't. Yes. 2 people, 3 people, 4, 5, 6, 7. Okay. Oh, 1 person didn't. No. Okay, interesting. Most people did. So the person who said they didn't learn it this way, can you unmute yourself and tell me what way you learned it?
So I learned it the 276 divided by 12, the one that you have it upstairs. And then we would say is equal to, and then we'll put a parentheses. And then we'll say 12 times, let's say 10. So this is like 120. So you subtract 120. So it's good. And then you do it again until you basically run out of.
Exactly. So doing repeated subtraction in some sense, which is actually also makes sense with this dots and boxes because you found a group of 12 there, group of 12 there, at the tens level, there's 120. And you keep subtracting groups of these pictures. So yes, that's lovely. Repeated subtraction is another way to do it. Gorgeous, gorgeous, gorgeous. I love the dots and boxes method because actually it now makes sense to me. But let me point out something. I'm going to just spend 5 minutes deviating from school arithmetic because what we were doing right now was all in base 10, a 10-1 machine with ones, tens, hundreds, thousands. And let me be really clear. 10 of these explode to make 110. 10 of these makes 100. That's really 10 tens. People call that 10 squared. And 10 of these, 10 squared makes 1,000, 10 cubed. So our base 10 system, based on our fingers, is all about the powers of 10. Martians wouldn't do, if you remember from a previous lesson, Martians have 3 fingers on 2 hands. They wouldn't do base 10, they'd do base 6, in which case they'd work with 1 and 6 and 6 squared and 6 cubed and so on. And Venusians, people on Venus, happen to know have 4 fingers on 2 hands. They would think 8's the correct number. So they would do an 8-1 machine. 1, 8, 8 squared, 8 cubed, and so on.
Okay.
My marker, hang on, there we go, back. Here's the thing. Let me now suddenly go to high school math. High school says, do you know what? We don't have to do base 10. We could do any base we like. In fact, but people love to call an unknown quantity the letter X. People are obsessed with letter X in algebra curricula. But it'll be the same thing. 1s, X's, X squareds, and X cubes. So this really was a 10-1 machine. It'd be 1, 10, 10 squared, 10 cubed. This really was Martian, a 6-1 machine, 1, 6, 6 squared, 6 cubed. So this is like all machines all at once. Now, when I was a high school teacher, I had to teach my students to do things like this. 2x squared plus 7x plus 6 divided by x plus 2. Take that weird looking thing called a polynomial, divide by that weird looking thing called a polynomial, and get an answer that's a weird looking thing called a polynomial. Now, we were just in grade 5. We were just doing this in grade 5. No warning. Everyone in this room, do this one. No warning. You're just doing high school maths all of a sudden. I've given you no years of experience in algebra. You're just going to do it. First thing is to have an emotional reaction. It looks scary. Be scared. Acknowledge that. Step number 2, take a deep breath like I did. Can I just do something? Can I do something? Anything to get going. Can I do something?
Can you just start making dots?
That's what I would do. Yes.
X plus 2 dots again.
Yeah, 2x squareds, okay. 7 x's and 6 1s. I agree. I mean, I don't know what to do, but that feels like a good thing to do. And you're right. This would be 1x and 2. So here's a picture of 2x squared from high school math, 7x plus 6. And we're looking for x plus 2s in that picture. Oh, can you find any 1 dot next to 2 dots in that picture? There's 1 dot next to 2 dots. There's 1 at that level. Any more? Yep, 1 dot next to 2 dots. Beautiful. I'm guessing that's Dilip. Is that you, Dilip? Excellent. If you have a photograph to share, we'd love to. If permission to share it, I'd love to be able to see it. All right, 1 dot next to 2 dots. 1 dot next to 2 dots. 1 dot next to 2 dots. That's 3 at this level. So it's 2 at that level and 3 at that level. So does that seem reasonable? So how do I read that answer? What's the answer? Two at the x level, 3 at the 1's level. It must be 2 at the x level plus 3 at the 1's level. 3 1s is just 3. Whoa. And guess what? Guess what? Look at that picture. Memorize that picture. Now look at this picture. Memorize that picture. They're identical pictures. They're identical pictures. What we just did in grade 5 or 6, whatever the level that maths is actually the same thing as year 11, year 12 maths. Actually, all this polynomial algebra work is just a repeat of grade 5, and no one tells kids that. Whoa, you've just done high school maths. In fact, look at this. If I told you x really was 10 all along, we've just done the number 2 times 10 squared, 200, plus 7 times 10, 76, divided by 10 plus 2 divided by 12. This will be 276 divided by 12. Apparently equals 2 times 10 plus 3, 23. which we know what we do because we did it. There it is, we did it. That's exactly what we did. So this division, this way of thinking about dots and boxes is actually high school maths in disguise. So when you get to your high school level math, please try to remember this day, October 21st. Keep this in your mind because your life will be so much easier as a high school student. Whoa, whoa. Okay, looks like we have about 8 minutes left together. I have to go back and explain the divisibility rule by 9. I need to finish today because I remember we're talking about this sort of thing. A number of these divided by 9, leaving same remainders as the number itself. So let me finish up today, see if I can explain the opening puzzler. Whew, what a crazy day. Here goes, here goes. I need to talk about divisibility by 9. We're now going to divide things by 9. So let me see what dividing by 9 looks like in a 10-1 machine. Let me go back to the 10-1 machine. Suppose I give you a picture with just one dot in it. That'll be what, 1, 10, 100,000. This is 10,000. This represents the number 10,000. If I want to divide by 9, I'm going to have to look for groups of 9. I don't see any right now, but I could unexplode. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 1 dot. So that gives me a group of 9. Great. But then I've still got this 1 dot left over. But I can find more 9s. So I can unexplode. 1, 2, 3, 4, 5, 6, 7, 8, 9, and an extra dot, 10. But that gives me another group of 9. I still have 1 dot left over. Oh, unexplode. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1 extra dot. Oh, there's a group of 9. Fabulous. Up, I still got 1 dot left over. Unexplode. 1, 2, 3, 4, 5, 6, 7, 8, 9. Dot. Up, there's a group of 9. But I still have 1 dot left over. I literally have a remainder of 1. So here's what I've just going to notice. If I start with 1 dot in, I'm going to do my work and be left with a remainder of 1 dot. It doesn't matter where that 1 dot is. If that 1 dot is here, I can see the same picture. Unexplode, 1 dot left over. Unexplode, 1 dot left over. I can see it's going to give me a remainder of 1 dot again. So 1 dot in a box gives me a remainder of 1 dot when I divide by 9. Oh, so if I take this number, 2 dots, 1 dot, 3 dots, and 1 dot. So that's 2, 1, 3, 1. Well, what I just said, if I divide by 9, if I divide this by 9, well, this dot here gives me a remainder of 1 dot. This dot here gives me a remainder of 1 dot. This dot here will also give me a remainder of 1 dot. Let's make my picture a little bit neater. These 3 dots here will each also give me a remainder of 1 dot. They count as 1 dot remainder, 1 dot remainder, 1 dot remainder. So actually, I can see, I'm going to have a remainder of what color am I going to do? Of these 2 dots here, there's the 2 dots there, plus this 1 dot here, remainder of that, plus these 3 dots here, remainder of that, there they are, and the 1 dot is already there. So my remainder, whatever the answer is, going to have a remainder of 2 plus 1 plus 3 plus 1. That's something. That's 5, 8, remainder of 8. Oh, that's the sum of the digits. Dividing this by 9 gives the remainder the sum of the digits. Because each digit is a dot, and each dot leaves a remainder of 1. All the dots I have in my picture are all going to bunch up in there as remainders. So when I divide a number by 9, the remainder has to be the same as all the dots bunched up at the end. It has to be the same as the sum of the digits. Whoa, whoa. Was that fast? That was fast. That was fast. The answer to that question is yes, that was fast. Let me do another one. Let me do one more. 3, 8, 7, 1, 4. I think did I do that earlier on? I don't know. 3, 8, 7, 1, 4. We know that each dot is going to appear over here as a remainder, appear over here as a remainder, appear over here as a remainder. So all 3 dots here will appear as a remainder. All 8 dots here will appear as a remainder. All 7 dots here will appear as a remainder. All 1 dot there will appear as a remainder, and all 4 dots there are already there. So I see I'm going to have a remainder of 3 dots and 8 dots and 7 dots and 1 dot and 4 dots. 11, 18, 18 and 5 is 23. 23. So I have a remainder of 23. Well, here's the thing. There's some more 9s in there. yes, I could find 9 plus 9 plus 5. So that's really the same as a remainder of 5. So actually, when you divide by 9, each dot becomes a remainder, and therefore the remainder must be the same as the number of dots you started with. This rule makes perfectly good sense to me now. Oh, I think I've hurt our brains. Have I hurt our brains? No, I haven't hurt your brains. Okay, then I'll do one final comment. One final comment. I started off today with this number, 387261, has a remainder of 0. It's divisible by 9. Here's the thing. If I reorder the digits, 872163 has the same sum of digits. It must also have a remainder of 0, divisible by 9. Or if I write the number backwards, 162783, it still has a remainder of 0 because it's the same sum of digits. This is freaky. The number 9 has the amazing property, you take a multiple of 9, rearrange its digits, it's still a multiple of 9. But have you ever noticed that? Like 45, that's a multiple of 9, rearrange its digits, the only thing you do is 54, it's still a multiple of 9. 81 is a multiple of 9. Rearrange its digits. 18 is everything you do. It's still a multiple of 9. Whoa. Here's my question. Is there any other number like 9 that has this amazing property? That if you rearrange a multiple of that number, rearrange the digits, you don't change it being a multiple. Someone's suggesting 3. What if 3 works that way? So maybe that's something to think about. I know the number 1 works that way. In a trivial way. Every number is divisible by 1, rearranges its digits. It's still divisible by 1. Okay, that's a cheap one. All right. What about 2? No, like 532 is divisible by 2, but rearrange its digits like, I don't know, 325. No, 2 doesn't have that property. Okay, so maybe 3 has that property. 1 has that property. 1, 3, check that one. 9. Any others? So on that note, I'm going to end on a mystery and say thank you so much for coming today. We're going to be back again in 167 hours and 17 minutes. So I hope to see you again in 167 hours and 17 minutes, as in like next week this time. Thank you so much for coming today. We will do decimals next time. Next time is going to hurt our brains. It's going to be a fast-paced lesson. So if you're up for it, come along. If you're not up for it, come along. There'll be something in it for you nonetheless. All will be grand and all will be good. So thank you very much for coming today. Really appreciate it. And thank you for being a joyous participant of Global Maths. Love it. Bye, everyone.